Okie doke. So for those people who are looking for more examples on implicit differentiation, this is your screencast. So let's see what we can do. For example, let's pretend that I want to find all points on the graph of x cubed plus y cubed is 3xy, where the tangent is horizontal. All points on x cubed plus y cubed is 3xy, where the tangent is horizontal. You may want to hit the pause button, try the 4 steps of implicit differentiation, and see what you can come up with. Or you may want to watch me do it. That's up to you, because you are watching, and I am not. I am not. That would be creepy. So here we go. We have to remember what it means to have a horizontal tangent. We're looking for where dy dx is 0. So, step 1 of implicit differentiation says we take the derivative of this with respect to x. The derivative of x cubed is 3x squared. Derivative of y cubed is 3y squared dy dx. On this side, we've got a product. The product rule is so much fun. It's 1 prime 2 plus 2 prime 1. And I'm just going to eliminate all the 3's because I can divide by 3 because 3 is not 0 no matter how much it tries. So then I'm going to collect the dy dx terms to one side and then kick that over to the other side. And then what? Well, then we suck out this dy dx and divide. So dy dx appears to be y minus x squared over y squared minus x. So what do I want? I want dy dx to equal 0, which means I want this to equal 0, which means I want this to equal 0, which means that that will happen whenever y is x squared. Whenever y is x squared on this curve. So we want a point on the curve. So I want to solve x cubed plus y cubed, see how I did that? Y cubed equals 3xy squared, no, 3xy. Boom. And if you solve that, you get that x cubed minus 2x, x to the 6th minus 2x cubed is 0. This factors very nicely. And you actually get 2 points on the curve. This one gives you the point 0, 0, and this one gives you the point cube root of 2, cube root of 4. Why? Because x cubed minus 2 is 0, okay. And then y is x squared, so we just square the radicand. Those are the 2 points on the curve. Now, you may be asking, how do I know if I'm right? Well, we could graph the curve. The curve's not hard to graph. Yes, that's the curve. And we could see that it's got a horizontal tangent at 0, 0, and it's got a horizontal tangent at cube root of 2, cube root of 4, which, by the way, is what you get if you superimpose the graph of y equals x squared on our graph. The places where y equals x cubed intersects the purple graph are the places where you get those horizontal tangent lines. And so that is a graphical verification of what we come up with analytically. Okay, I'll do one more. Let's find all vertical and horizontal tangents to 3x squared plus 4y squared plus 3xy equals 24. The locations of all of the vertical and horizontal tangents. And that's not too bad. We're just going to differentiate both sides with respect to x? 0! Okay, good. You got that. You got the right side. Good for you. So we'll look on the left side. This is 6x. This is not too bad. This is 8y dy dx. And this is a product rule. 1 prime 2 plus 2 prime 1. And from here, I think we can do a couple things at once. We can collect the dy dx terms, suck and divide, and know what dy dx is going to be. The 6x and the 3y are going to be over there, and we will divide by 8y plus 3x. So, two questions to consider here. One is the question of vertical tangents. Well, vertical tangents are places where the derivative is undefined, which means that the denominator would have to be 0. And that's going to happen where y is negative 3/8 x. So then what we do is we do a little bit of algebra. We stick that negative 3/8 in place of the y's and solve a quadratic equation. It's a quadratic equation of the form blah x squared equals blah bitty blah. And you can solve that to get that x is plus or minus radical 112 over 35. You really can, and you probably should. The other question is the question of the horizontal tangents. And the horizontal tangents happen where the derivative is 0, which means I want the derivative to equal 0, which means that y is negative 2x. And then we solve this by substituting in for every y and solving a quadratic equation. And using a little bit of algebra, it's not too tricky, y turns out to be plus or minus radical 96 over 13. Very guessable. You would have guessed those values even if I didn't give them to you. You should, just to be rigorous, check to make sure that these values make the derivative undefined and not indeterminate. These values make the denominator 0 while the numerator is non-zero. These values make the numerator 0 while the denominator is non-zero. And it should be asked, does this even make sense? Well, the graph is an ellipse that's been rotated about the origin. That is an ugly ellipse, but that's the basic idea. And so sure enough, you get vertical tangents at the places where you would expect, and you get horizontal tangents at the places where you would expect. Okay, so I'll throw in one more just for good measure. Sort of an on your own, though. I want to find the second derivative if xy squared plus y minus 2 is 0. The second derivative. So hit the pause button. Not yet. When you hit the pause button, find dy dx, and then take the derivative of that to see what the second derivative of this function is. Well, it's not a function. The second derivative of this equation, y with respect to x, is. So here, hit the pause button. Okay, so let's see. I'm looking for dy dx, and I'm pretty sure that you figured out that that's negative y squared over 2xy plus 1. And so now you're thinking, well, I need the second derivative. The second derivative, that's quotient rule. It's the bottom times the derivative of the top. The derivative of the top is negative 2y times dy dx. Well, what's dy dx? This is dy dx. Right? Minus numerator times derivative denominator, and that's 2x dy dx. That's a 2xy plus 1 plus 2y over 2xy plus 1 squared. So even with the second derivative here, we have quotient rule. denominator times derivative numerator. Derivative numerator contains a dy dx. dy dx is something that we know. It is something that we know. Minus numerator times derivative denominator. Derivative denominator contains this dy dx that we can substitute in. And then how do we clear that up most easily? Well, we clear it up most easily by multiplying through by this 2xy plus 1. Oh, this is going to be a mess. And then the denominator also gets multiplied by 2xy plus 1. Okay? Okay. So hopefully that's enough practice to get you going, and we'll see you soon.